How Zener diode and light-emitting diode LED functions in electronics. A diode is a two-terminal electronic component that allows current to flow in one direction only. It acts as a one-way valve for electric current, permitting current to pass through it in the forward direction while blocking current in the reverse direction. Diodes are widely used in various electronic circuits for rectification, signal demodulation, voltage regulation, and protection purposes. There are several types of diodes, each with its specific characteristics and applications. Some of the common types of diodes include Zener diode. ChatGPT. A Zener diode is a type of diode that is specifically designed to operate in the reverse breakdown region, which means it can conduct current in the reverse direction when a certain voltage, known as the Zener voltage, VZ, is reached. Unlike regular diodes, which are designed to withstand only a limited reverse voltage before breaking down, Zener diodes are intentionally doped to have a narrow depletion region, allowing them to function reliably in this breakdown region. The key characteristic of a Zener diode is its ability to maintain a relatively constant voltage drop across its terminals when operated in the reverse breakdown region. This makes Zener diodes ideal for voltage regulation and stabilization applications. When the voltage across the Zener diode reaches or exceeds its Zener voltage, VZ, it starts conducting in the reverse direction, preventing the voltage from rising above the Zener voltage value. Applications of Zener diodes include voltage regulation. Zener diodes are commonly used as voltage regulators to provide a stable reference voltage in electronic circuits. By placing a Zener diode in parallel with a load, the voltage across the load can be maintained at a constant value, even if the input voltage varies. Voltage shifting. Zener diodes can be used to shift the voltage level of a signal by clamping it to a specific voltage level. Overvoltage protection. Zener diodes are employed in various circuits to protect sensitive components from overvoltage conditions by diverting excess voltage away from those components. Voltage measurement. Zener diodes are utilized as voltage references in measuring instruments and sensors. Zener diodes come in various voltage ratings, and their Zener voltage can range from a few volts to several hundred volts, depending on the specific application. It's crucial to select the appropriate Zener diode with the desired Zener voltage and power rating to ensure proper performance in a given circuit. Voltage regulation refers to the process of maintaining a constant output voltage level in an electronic circuit or power supply, regardless of changes in the input voltage or load conditions. It is essential in various electronic devices and systems to ensure stable and reliable operation of the components. In many applications, the input voltage may vary due to fluctuations in the power source or changes in the load being driven by the circuit. Without proper voltage regulation, these variations can lead to undesirable consequences, such as improper functioning of electronic components, data corruption, or even damage to sensitive devices. Voltage regulation can be achieved using various techniques and components, with Zener diodes being one of the popular choices. Some common methods for voltage regulation include Zener diode voltage regulation. As mentioned earlier, Zener diodes are commonly used as voltage regulators. By connecting a Zener diode in parallel with the load or across a voltage reference, the Zener diode clamps the voltage to its Zener voltage value, providing a stable output voltage. Linear voltage regulators. Linear voltage regulators use active semiconductor devices, such as transistors, to regulate the output voltage. They come in two main types, series and shunt regulators. Series regulators operate by varying the resistance between the input and output, while shunt regulators divert excess current away from the load. Switching voltage regulators. Switching regulators work by switching the input voltage on and off at high frequencies, and then filtering and regulating the output voltage. They are more efficient than linear regulators but are more complex. IC voltage regulators. Integrated circuit IC voltage regulators are specialized chips that incorporate all the necessary components for voltage regulation. They are available in fixed or adjustable output voltage configurations. PWM, pulse width modulation, voltage regulation. PWM is used in some power supplies and motor control applications to regulate the output voltage by varying the duty cycle of the output waveform. The choice of voltage regulation method depends on factors such as efficiency, power requirements, cost, and complexity of the circuit. Voltage regulators are used in a wide range of applications, including power supplies for electronic devices, microcontrollers, sensors, communication systems, and many other electronic circuits. They play a crucial role in maintaining stable and reliable operation in these systems. Voltage shifting, also known as voltage level shifting, is a technique used to change the voltage level of a signal from one voltage reference level to another. It is commonly employed in electronic circuits when interfacing components or systems that operate at different voltage levels. Voltage shifting is essential to ensure compatibility and proper signal communication between different parts of a circuit. There are several methods to achieve voltage shifting, and the choice of technique depends on the specific application and requirements. Some common methods for voltage shifting include voltage divider. A voltage divider circuit consists of two resistors in series connected across the source voltage. The output voltage is taken from the junction between the two resistors, which can be adjusted to provide the desired voltage level. Op-amp level shifter. Operational amplifiers, op-amps, can be used to shift the voltage level of a signal. A simple op-amp level shifter can be constructed using an inverting or non-inverting amplifier configuration, which amplifies the input signal to the desired output voltage level. Level translation ICs, specialized level translation integrated circuits, ICs, are available that can shift signals between different voltage levels with minimal additional components. These ICs are designed to handle bidirectional signal shifting and are commonly used in mixed voltage systems. Digital logic level shifting. In digital circuits, level shifting is often necessary when interfacing components that operate at different logic voltage levels, example 3.3V and 5V. Level shifting can be accomplished using dedicated level shifting ICs or with simple transistor-based circuits. Zener diode clamping. As mentioned earlier, Zener diodes can be used to clamp a signal to a specific voltage level, effectively shifting the signal's reference voltage. Transformer coupling. In some cases, transformers can be used to shift the voltage level of signals, particularly in communication systems or audio circuits. It is important to ensure that the voltage shifting technique used does not introduce distortion or affect the integrity of the signal. Additionally, attention should be given to factors like signal bandwidth, noise, and power consumption while implementing voltage shifting in electronic circuits. Voltage shifting is a fundamental aspect of circuit design, especially in mixed voltage systems or when interfacing components with different voltage requirements. Proper voltage shifting ensures smooth signal transmission and compatibility, contributing to the overall functionality and reliability of electronic devices and systems. Overvoltage protection. Overvoltage protection is a mechanism used in electronic circuits and systems to safeguard sensitive components and devices from excessive voltage levels that could lead to damage or malfunction. Overvoltage events can occur due to various reasons, such as power surges, lightning strikes, faulty power supplies, or circuit failures. Overvoltage protection circuits are designed to detect and respond to these situations, preventing voltage levels from exceeding safe operating limits. There are several methods for implementing overvoltage protection, depending on the specific application and the level of protection required. Some common techniques for overvoltage protection include Zener diode clamping. Zener diodes can be used as voltage clamps to limit the voltage across a load. When the voltage exceeds the Zener diode's breakdown voltage, Zener voltage, it starts conducting and diverts the excess current away from the sensitive components, protecting them from overvoltage. Gas discharge tubes, GDTs are devices that have a high breakdown voltage and low capacitance. They are used for high-energy overvoltage protection in applications such as power lines and communication systems. When the voltage exceeds the GDT's breakdown voltage, it forms a low resistance path for the surge current. Metal oxide varistors, MOVs, are components that have a nonlinear voltage current characteristic. They have a high resistance at normal voltages but become highly conductive when exposed to excessive voltage transients. Transient voltage suppressors, TVS diodes, are semiconductor devices specifically designed for overvoltage protection. They respond quickly to transient overvoltage events and provide a low resistance path for the excess current. Overvoltage crowbar circuit. The crowbar circuit is a protection circuit that uses a thyristor or other switching element. When an overvoltage event is detected, the crowbar circuit triggers, short-circuiting the power supply and protecting downstream components. Fuses and circuit breakers. Fuses and circuit breakers are protective devices used to interrupt the flow of current in case of overcurrent or overvoltage situations. They are commonly used in power distribution systems to protect against surges and faults. Electronic overvoltage protection circuits. Sophisticated electronic circuits, such as voltage detectors, comparators, and voltage regulators, can be used to monitor the voltage levels and trigger protection mechanisms when an overvoltage event is detected. The choice of overvoltage protection method depends on factors like the magnitude of potential overvoltage, response time requirements, cost, and the specific application. Properly implemented overvoltage protection helps enhance the reliability and lifespan of electronic devices and prevents costly damage or failures due to voltage surges. Voltage measurement. Voltage measurement is the process of determining the electrical potential difference between 2 points in an electrical circuit or system. Voltage is a fundamental electrical quantity that represents the potential energy per unit charge at a specific point in the circuit. It is usually measured in volts, V. Voltage measurement plays a critical role in electronics and electrical engineering, as it allows engineers and technicians to understand and analyze the behavior of circuits, troubleshoot issues, and ensure proper operation of devices and systems. There are various methods and instruments used for voltage measurement, depending on the level of accuracy and the specific application. Some common methods and instruments for voltage measurement include multimeters. Multimeters are versatile handheld instruments used for measuring various electrical quantities, including voltage. They come in analog and digital versions and can measure both AC, alternating current, and DC, direct current, voltages. Multimeters often have different voltage ranges, allowing measurements from millivolts to kilovolts. Voltage probes. Voltage probes are passive devices connected to a multimeter or an oscilloscope. They are used to make direct voltage measurements at specific points in a circuit. Voltage probes have different attenuation factors and bandwidths for measuring various voltage levels and signal frequencies. Oscilloscopes. Oscilloscopes are electronic test instruments used to visualize and analyze electrical signals. They can display voltage waveforms in real time, making them valuable for measuring time-varying signals, AC voltages, and transient events. Voltage dividers. Voltage dividers are simple circuits consisting of resistors used to scale down voltage levels for measurement purposes. They are commonly employed when the voltage to be measured exceeds the range of the measurement instrument. Data acquisition systems, DAQ systems, are used for automated voltage measurements in various applications. They consist of hardware modules and software that can acquire and record voltage data from multiple points in a system simultaneously. Voltage sensors. Voltage sensors are specialized devices that can measure voltage levels and provide analog or digital outputs. They are used in various control and monitoring applications. Potential transformers, PT, and voltage transformers, VT. These are used in high voltage systems to step down voltage levels for measurement and protection purposes. When performing voltage measurements, it is crucial to select the appropriate measurement method and instrument, considering factors like the voltage range, accuracy requirements, signal type, AC or DC, and any potential safety considerations. Proper voltage measurements are vital for diagnosing faults, calibrating equipment, and ensuring the safety and performance of electrical and electronic systems.